My book, Programming the Universe, indeed is about the universe being a giant computer, which really sounds goofy, you know. Whenever I say that, I say, did I really say that? But I just wanted to say that the reason for writing this book was that I have spent the last decade of my life as a quantum mechanic, basically talking with atoms, trying to convince them to store information and to process that information, trying to get them to compute. And along the way, I realized that, in fact, everything out there is computing all along. And we're just kind of hijacking this computation when we build quantum computers. All right? So my experience of this, you know, this scientific claim that the universe is a giant computer really comes out of a kind of a very hands-on working with atoms and making them compute. And for the middle part of this talk, I will actually tell you how to build quantum computers. The folks at PI, and particularly at Waterloo University, thanks to the generosity of Mike Lazaridis, now have one of the world's greatest programs in quantum computing. And if you want to see some quantum computers in action, you should go down to Waterloo and take a look. They look really cool, like these gigantic beer kegs, super cooled with liquid helium, with millions of dollars of electronics snaking out of them. And they also do cool things. They don't just look really cool. Okay? All right. So what I'm going to talk to you about comes from my hands-on experience as a quantum mechanic. But I hope to convince you by the end of this talk that, in fact, there are literally cosmic implications of talking to atoms and figuring out how to make them to compute. Let's step back from quantum computing and quantum mechanical engineering, and let's look at the world as a whole. So it's no secret that we're in the midst of an information processing revolution. And by the way, I'm going to draw lots of goofy pictures during this talk, and you're just going to have to put up with it. That's just the way things are. So this is my picture of a computer, a laptop computer. This is my unpaid solicitation for... Right? It's no secret that we're in the midst of an information processing revolution based on digital computation, electronic circuits, and optical communication, right? And this is a very important thing in our life. And you know, well, not that important. I mean, sometimes I think it gets overemphasized. But if you look in the guts of something like this, so if you were to open this up and look inside, and interestingly, as a professor of mechanical engineering, computers are about the only mechanical device that people actually open up any longer, right? To put in new memory and stuff like that. If you open up your toaster, it voids the warranty. But actually, people are encouraged to open up computers. In fact, my senior colleagues in mechanical engineering at MIT complained that their incoming students have never even used a screwdriver. And that's not true. At least 2/3 of them have used a screwdriver to open up their computer to put in more memory. Okay, so what happens if you look inside one of these computers? You'll find that information is stored on bits. What's a bit? Well, a bit is just a distinction between two possibilities, which are conventionally called 0 and 1. So let's call 1 as 0. And what I'm drawing right here is just a little picture of what's called a capacitor. And a capacitor is like a little bucket for electrons. And if there are no electrons in the bucket, you call that a 0. And then if you put a bunch of electrons in the bucket, this is my picture of electrons. For some reason, I think of electrons as being blue. And I've been going around telling people this for a long time. Sorry, I should take this off here. I've been going around telling this people for a long time. But then a famous blind Italian physicist named Paolo Rossi, who has been blind since birth, told me that this is wrong. Electrons are yellow. Don't ask me why. That's just the way things are. And so electrons off the capacitor, out of the bucket, are 0. Electrons on the capacitor, electrons in the bucket are 1. And to flip a bit, to change it from 1 to 0, for instance, you just empty the electrons out into the ground, right? And now the bucket is empty, and you have 0. And all at bottom of a computer is a set of switches to fill up buckets of the electrons. And let me actually tell you, in your hard drive, actually, so if you have an old iPod as opposed to a new iPod Micro, what happens is you have these little magnets. This is like a picture of a magnet with a north and south pole. Magnets come from circulating electrical charges. That's what this thing is right there. And if we can call magnet with the north pole up 0, and magnet with the north pole down, with the little charges circulating the other way, we can call that 1. And so inside your hard disk, bits are stored by little magnets. The point is that every time you have some system that can have one of two distinct states, it can store a bit of information. All right? And in fact, in fiber optic communication, if you've got a bunch of photons coming into this fiber optic communication line, pulse of light can be 1, no pulse of light can be a 0. This would not make a very good. Fiber optic communications line should always be the same width. This is not a very good one. 0, here's a 1, here's another 1, here's a 0, here's another 1. Okay? So basically, this information processing revolution comes about because people have developed ways using electronics and optics to store bits of information digitally. And all your computer is doing, even the most complex computation it's doing, like playing Doom or something like that, right? That just involves busting up the information you're putting into the little bits, storing them at this microscopic level, and then flipping those bits really, really fast, billions of times a second. Okay? Everybody happy with this? Have you reached the point? These guys have a pool for the minute in which I say the first completely incomprehensible thing. Am I there yet? Okay, that's right. They wouldn't give me money to tell them what a time is, because then I could make it as incomprehensible as possible, right? All right, so everybody's fine about this. Okay, but this information processing revolution, I claim, is still, despite its many consequences for the world, which indeed are great, is still not as important and has had not as great an effect on the universe as the previous big information processing revolution, which is the invention of the printed word. Mind you, there are lots of, information processing revolutions. I'm just touching on some high ones. Of course, the invention of television is very important. As I told the television reporter this morning, and the invention of radio is very important, as I was telling the radio people this morning. So, but the invention of the printed word is an extremely important invention in human history. And it's had a far greater effect on human beings than the invention of computers so far. And if I didn't believe that, why the heck would I write a book, okay? All right? And it made information accessible to millions of times more people than information had been accessible to before. It created the possibility of having literate societies, which I know that these people sitting in the front row think is very important. It changed the world entirely. And it's based on the technology of printing. It's based on a technology, actually in some sense a more complicated technology than that of computation, as we'll see in just a second. Well, that's of course very important, but of course then, there have been lots of other information processing revolutions, and I think that we can say that without much hesitation that, if I can do this while drawing at the same time, that the invention of the written word was a remarkable information processing revolution, perhaps more important than the invention of the spoken word, of the printed word. So let me do some written words here. So, whoops, sorry. I never can get these accents in the right place. I always forget my ancient Greek. It's been a long time since I looked at it. Okay, in arche en ho logos, in the beginning was the word, the beginning of the gospel according to John. Right? Now, the written word is a huge was and is a huge information processing revolution, and quite bizarre. Who would ever thought to take sounds and say, oh, we're going to like little scratches on pieces of, for instance, tile or ceramic to represent these sounds? What a bizarre idea. Of course, actually, if you look at these very first texts, like the ceramic texts of Linear B from Mesopotamia, there are things like, you owe 20 shekels in taxes, pay it now, right? That's exactly the kind of thing they say. Particularly painful around this time of year in the United States. And that shows you, in fact, why one of the reasons that writing is so important as an information processing revolution. It was writing that allowed us to have centralized societies with division of resources between different places, for better or worse, okay? Which makes human beings quite different from other animals. No matter how intelligent they are, having writing makes a huge difference. All right, you can kind of see where I'm going, because, of course, the next one is, well, hey, the written word was a big invention. What about the spoken word? I mean, come on, the spoken word. What makes human beings human? It's the fact that they can speak to each other, that they can talk, and that they can put things into words. that we have words is what makes us human. Because in fact, and I should say, the universal language that goes along with it. Because other animals have utterances, very complicated ones, for instance, in the case of humpback whale songs, right? But there's no evidence there that these utterances by other animals actually possess the same power of human language. Because human language is not merely a way of referring to things, it also includes in it a way of reasoning, a way of thinking, the notion of logic. Indeed, computer languages, which are, we made computers in our image by giving them language. Things like Java, right? Computer languages are also universal. So ironically, the only other thing out there with universal language that we have right now, for sure, are computers. I'm not saying that computers are human, though in fact, many of my students at MIT seem to regard their computer as their best friend. And I know that computers are very human in their ability to mess with my mind, right? So they're getting better and better at it. All right, so the spoken word, extremely important, but of course you wouldn't be able to have the spoken word if you didn't. I know these pictures are very goofy. Please bear with me, Mitchell, okay? I'm operating under pressure. I'm trying to write and draw, talk and draw at the same time. And this is my picture of a brain, right? You can't talk or think if you don't have a brain. Actually, that's not true. I know that's not well, no, sorry. Excuse me. You're probably. This might be an example, right now. So, the brain is a very remarkable invention in information processing technology. Invented, of course, by natural selection. Okay. And Pache, any creation science people in the audience, we can talk about that later, all right? But invented somehow by this process of natural selection, which we'll describe in a bit, that allows you to have centralized processing in a way which in fact is very digital, because the brain has these neurons that are sending signals back and forth, pulses of electromagnetism back and forth. They have synapses which are absorbing chemicals which are also digital in their nature. It's a remarkable feat of digital information processing. Sorry, have I lost you guys yet? We're not there? Okay, great. Okay, and of course we wouldn't have the brain if we hadn't come to, this is my personal favorite information processing revolution. My favorite information processing revolution, you'll see what it is in just a second, is the sexual revolution. These are little sperms that are wiggling their way towards an egg. This one's very happy because he got there first, right? The sexual revolution, not the one from the 1960s. I was a little young to actually take full advantage of the first sexual revolution. But the one some 500 or a million years ago when organisms discovered sex. Now, what's so great about sex? I mean, apart from the obvious things, right? Okay, so, and I should mention, if you do buy my book, there's lots more about sex in it. Okay, so. Though the publishers maybe take out some of those pictures, right, as you can see. All right, so what's so great about sex from the point of information processing? Well, if you compare it with asexual reproduction, so if you take some bacterium that's reproducing asexually, and bacteria have sex too, it turns out everybody has sex, they just weren't telling us about it, okay? But let's take something reproducing asexually, then the only way to change is to have mutations, changes in your genome, generally caused by something random, by like, say, radiation coming in from the outside. And change is actually bad, because 99.9% of those mutations, of those changes, are going to mess you up. The bacteria that carries, the offspring that carry this mutant genome will be worse off than the parent bacterium. And that's bad. And there's really not any way to get around that, because if you're reproducing asexually, really you have to try to reproduce your genome as exactly as possible. Most bacteria reproduce 9 out of 10 of their offspring are genetically identical to them, down to the last little piece of DNA, genetically identical. So you can't really change very much. Now, here's where sex comes in. So this is, I should say, this is what's called in the engineering department at MIT a coupled design. You have 2 functions. One is maintain the integrity of the genome. The other is evolve, create variation. But these are coupled together, and you can't vary one without screwing up the other. Okay? That's a coupled design, and that's bad. Coupled designs are bad. Now, what does sex do? Well, at first, sex sounds like a really bad idea. And indeed, when I was much younger, my mother told me to wait, hold off. It's not such a good idea right away. But sex is a bad idea because when you have offspring, your genome, no matter how successful you are, is never passed on intact. So sex messes with success. I also like to think, since I have children, also like to think that this allows me plausible deniability as well. It has its advantages, okay? So sex messes with success. But what's good about it? Well, what's good about it is during reproduction, after my parents had sex, their genes got all scrambled up in some random order, and we'll talk more about that later, how that happens. And I got some combination of them. What's happening is that genetic variation is being injected into the reproductive process, and a lot of genetic variation. I don't have any degree in mechanical engineering. I never even studied biology in high school. You don't let that happen here, right? But I did write several papers and publish them in biological journals, and one of them was comparing the raw genetic information processing power in terms of generating variation, genetic variation, of 1 trillion bacteria. That's many swimming pools full of bacteria, reproducing every 30 minutes, okay? But at this rate where 9 out of 10 of the offspring have the same genome. Compare this with a small town of about 1,000 people, like my parents' town in Vermont. Actually, theirs is about 300 people, but that's okay. 1,000 people who can select their mates from the town, who have children once a generation every 30 years or so, and who are having sex and undergoing recombination of their genes. You find out that the town of 1,000 people is as strong genetically in terms of generating variation as these many swimming pools full of bacteria. It's very powerful. Actually, anybody who watches American daytime television would know about this already. I mean, the number of possibilities is just incredible. Okay, so, and then, if we go further back, then you may not be able to tell with this, we come to the grandmother, the mother of all information processing revolutions, which is, of course, life itself. And here I'm trying to draw the nucleus of a cell. I'm trying to draw, not with very little success, a double helix, which is a form of the DNA. Here's maybe some kind of, protein sheet for alpha sheet for some protein. You can tell I never took biology, right? And there are these cells often have these hairy-looking molecules that sit off the outside, okay? What's going on inside a cell? Well, information processing is what's going on inside a cell. And that's what people have known for 50 years. The DNA stores genetic information. When it gets expressed, it sends out messenger RNA to say, hey, build this protein or build this other protein. These hairy things on the outside are, in fact, for when some funny little molecule comes in, if it's the right kind of molecule, it will bind to this, and then a pore opens up and sucks the thing in, okay? It's about signaling. They're called locks and keys, these mechanisms. It's about information. Life is about information. So life, however it happened, discovered information processing at the atomic scale 5 billion years ago, 4 to 5 billion years ago, whenever it happened on Earth. I don't know where it happened elsewhere, or if. It didn't happen more than 5 billion years ago on Earth, because Earth is only 5 billion years old. Right? So life is on one heck of an information processing revolution. My goodness, right? We wouldn't be here without it, but I mean, also, it's just a remarkable thing. And this is why biology is so fascinating, and I wish I actually had studied it at least maybe in junior high school, okay? Surely, this is the big one. What could be a bigger information processing revolution than life itself? I mean, this is really magnificent. Not my drawing, but the thing, this is really magnificent. Life, it's amazing. It's incredible. Well, actually, I'm here to tell you, no, that's not true. If we look at these information processing revolution, each one builds on the techniques of the previous one. Sex builds on life, brains build on sex, language comes from sexual reproduction, written word comes from language, our notion of building computers comes from our ability to manipulate ideas. They all build on their previous information processing revolutions. Now, life only showed up, 4.5 billion years ago or something like that. The universe is 13.8 billion years old. What about that, what about that previous, well, circa like 9 billion years or so? What was happening then? My claim is that the information processing revolution, which is life, and all subsequent ones, and what's ever going to come next, and I have no clue as to what's come next. All I know is it's going to be funky. I went to a James Brown concert once, and somebody yelled, "Jim, what are you going to play next?" And he said, "I don't know, but whatever it is, it's got to be funky." It will be funky, that's all I can say. All right? My claim is that the first information processing revolution began at the Big Bang itself. The Big Bang occurred 13.8 billion years ago, went kerblooey, vast amounts of stuff, elementary particles were produced. Then they produced things like, galaxies. And I should probably try, they give me too many, when you have too many colors of these pens, then you're tempted to use them. Things like suns, planets, etc. The Big Bang, I claim, was not just a Big Bang, it was a bit bang. Sorry, I know that's a really dumb joke, but I figure, and there are many more dumb physics jokes in this book. I tell you, if you want, there's a whole. If you were to string them all together, you could have like a 20-minute monologue that would have everybody completely out the door. All right. So the Big Bang was about information. Now, how is that so? Well, every atom, every elementary particle, carries with it bits of information. A few tens of bits per atom or elementary particle. This has actually been known for a very long time. We'll talk about it more in just a second, all right? So I haven't lost you guys yet. Whenever they collide, those bits flip. At its most microscopic and fundamental levels, the universe is processing information. And as we'll see in just a second, processing information in a digital fashion, registering bits and flipping those bits. The universe computes. And it's been doing so ever since it began. And it's this computational ability of the universe, this computational capacity of the universe that's responsible for all other information processing revolutions. Every one of those builds off, from life up to building quantum computers. We can do that because the universe is already processing information. And when we actually go in and talk to these atoms, and I'll tell you how to do that in just a moment, and tell them and ask them nicely to compute and make them compute, what we're doing is not actually suddenly making the universe compute at the atomic scale. We're taking the computation the universe is already performing at its most microscopic scales, and we're hijacking it. We're essentially hacking the universe, right? Which would have been a good title for my book, except that if you translate hacking the universe into Japanese, it sounds somehow, I don't know, dangerous, right? So we're hacking into the existing computation in the universe, and we're turning that computation to make the universe do things like perform quantum computations. So that's what we're doing. And this information processing revolution of quantum computation, like all ones previously and like all ones subsequently, comes out of this underlying computational nature of the universe. When I talk with people in humanities, they think that information must have meaning. And, it would be nice if information had meaning. Though, again, the example of daytime television in the United States does kind of put the lie to that, I'd say. One of the great discoveries of the 20th century was the discovery of how to quantify information in terms of bits, really made primarily by Claude Shannon at AT&T and MIT, Norbert Wiener at MIT. They discovered that the quantity of information was distinct from the meaning of information. I mean, what does information mean? This is a tough one. I actually have a master's degree in philosophy from Cambridge University, so you could call me Dr. Philosophy, right? Because Dr. Science has a Sorry, never mind. People don't know this anymore. So I quit because I couldn't understand what the heck people were talking about in philosophy. You go to a seminar and one person would say blah, 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 and then another person would jump up and say, "You're absolutely wrong. The truth is blah, 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 blah." And I'd go, "Didn't they just say exactly the same thing?" So I went to physics where, things were easier. But meaning is something that the meaning of meaning has eluded philosophers and everybody else for thousands of years, as long as people have even thought about meaning. So meaning, like the meaning of a bit on its own doesn't mean anything. So like yes, right? Yes could be the answer to the question, will you marry me? Or it could be the answer to the question, do you want fries with that, right? Now, it means something very different in both cases, and it has nothing to do with the bit itself. So my personal perspective, an engineer's perspective on meaning, not a philosopher's, is that meaning is as meaning does. So for instance, as we'll see, one use of a bit in a computer is to tell the computer to do something. So the computer takes in a bit of information and interprets it. So zero, the computer interprets 0 to mean do this, like add 2 plus 2. Or interprets 1 to mean do that, like add 3 plus 1, right? So meaning has to do with interpretation. That's all I'm going to say about it. Let me tell you how quantum computers work. So what we want is we're going to have here a brief course in quantum mechanics. So quantum mechanics in 5 minutes. And then there will be the quiz, and then you can all go home, right? Now, the important thing to remember about quantum mechanics is that quantum mechanics is weird. This is a technical term. It means like funky, right? Like James Brown, right? It means weird. That's what it means. It's very hard to understand. It's counterintuitive. It's strange. Niels Bohr, who was one of the founders of quantum mechanics, said, anybody who thinks they can contemplate quantum mechanics without getting dizzy hasn't properly understood it. Of course, he said it in Danish, which was more impressive, right? But, but I don't know what it is in Danish, right? And one of the central weirdnesses, and famously, you know, there's this phenomenon where people who get their Nobel Prize for quantum mechanics, like Einstein got his Nobel Prize for quantum mechanics, never believed in it. God doesn't play dice, he says. He was wrong, right? God does play dice, as we'll see in just a second. So quantum mechanics is, and of course, one of the reasons that he didn't want to believe in it because it was counterintuitive, and if anybody had the right to trust their intuition, it was Einstein. So his intuition told him wrong, it can't be true, and so he trusted it, and he was wrong as a result. Okay, so what is quantum mechanics about? So it's about what the central kind of weirdness is what I'll call wave-particle duality. Wave-particle duality. Ooh, it sounds pretty weird, doesn't it? You know, that was made up by Niels Bohr. And what it says is that stuff we think of as waves, like light or sound, are actually made up of little particles, and the particles of light are called photons, Greek for light things, and particles of sound are called phonons, Greek for sound things, right? This is my picture of a particle right here. Similarly, particles, things like electrons, atoms, or for that matter, hockey pucks, right, have waves that correspond to them. And these waves are solutions to what's called the Schrödinger equation. Now, you can't say you didn't understand that just because it's some German word with an umlaut in it, right? That's right. And I'm not going to write it down, okay? So what does this mean? Well, for the light having particles associated, what it would mean is the human eye is an extremely good detector of light. It can your eye will respond to single photons. So a single particle of light. Actually, interestingly, your brain doesn't respond to single photons because there's some filtration that takes place in the optic nerve. You only respond to like 5 photons. And there's a good reason for that, because otherwise, even if we were pitch black, you'd be seeing flashes of light all the time, just because you're hot and your own eyes are generating photons. Frogs, however, do perceive single flashes of light. For some reason, this wasn't activated. And so suppose for a moment that I'm a frog, all right? And I'm a frog, and we turn down the lights of this room. Things look continuous. The lights are very bright, for me particularly. But as we go on, the lights get dimmer and dimmer and dimmer and dimmer. And at a certain point, what would happen, and instead of seeing them get dimmer, I'd start to see individual flashes of light. And those are photons. They're individual particles of light. Okay? Now, how about these funky waves that correspond to particles, to electrons and atoms? And this is where quantum mechanics and quantum computation comes in. So suppose I have a wave like this. These waves have to do with where things like electrons are. So this means, say, electron over here. Okay? This wave says electron's kind of over here. Here's another wave which says electron is over there. Okay? And indeed, you see that this could be a quantum bit, because remember that in our initial picture of bits in a computer, what is a bit in a computer? It's just like a whole bunch of electrons over here, out of this bucket, that's 0. A whole bunch of electrons over here, in this bucket, that's 1. So this is kind of taking a bit and miniaturizing it to the single electron level. And this is actually not that hard to do with current technologies. So we'll call electron over here 0 and electron over there 1. So far, that doesn't seem so strange. So the wave has something to do with where the electron is. Big deal. The problem is, and here's where the weird counterintuitive stuff comes in, is that the waves that correspond to electrons can add up, just like water waves or sound waves or light waves. So if this is an okay for an electron, and this is an okay wave for an electron, then so is this. And this is a wave where the electron is, in some funny quantum sense that nobody understands, it's here and there at the same time. It registers 0 and 1 at the same time. Now, people are looking at me knitted with brows, and that's important. Good. This is good. This should make you dizzy, right? Now, and don't look at me like I understand this either, okay? Because I don't. You know, when I was 20 years younger, I thought it was extremely important to understand this, and that's why I did this master's degree in philosophy of science, studying the philosophy of quantum mechanics at Cambridge. I didn't understand it before, and I didn't understand it afterwards. And now, you know what? 20 years down the line, I think I've come to accept this. Right? It's like, I don't understand it, but neither does anybody else. You know, I'm okay, you're okay, right? So it's okay. It's okay. All right? So quantum bits, also called qubits, can register 0 and 1 at the same time. Well, I don't know what that means. But the nice thing about being an engineer, or at least a professor of engineering, is you don't have to understand it in order to make it work. All right? So I don't know what that means, but I know what I can do with it. And what can I do with it? I can build a quantum computer. So for instance, suppose that 0 tells my computer to add 2 plus 2. And we'll see in just a second. I'll describe briefly, because I don't have that much time, how quantum computers work. And suppose 1 says, OK, add 3 plus 1. And it's not that hard just to take, say, a bunch of atoms in a molecule. They're storing bits of information already. They interact with each other at the molecular scale. They're 1 angstrom apart, 10 billionth of a meter within this molecule. If you zap them with light, you can make them compute. It's not that hard to make them, add 2 plus 2, add 3 plus 1. Indeed, if people had thought of doing this, they could have done it back in 1950. Strangely enough, but they didn't think of doing this. It wasn't until 10 years ago that I pointed out that you could do this, all right? So that's fine. 0 says add 2 plus 2. 1 says add 3 plus 1. But what about a computer where I put in this quantum bit, which is 0 and 1 at the same time? This quantum computer. This quantum computer then adds 2 plus 2 and 3 plus 1 at the same time. It does this and that at once. Quantum computers have this intrinsic multitasking ability that ordinary computers don't. Why? Because their bits are quantum mechanical, and because these quantum bits, for reasons nobody understands, can be 0 and 1 at the same time, just because electrons can be here and there at the same time. As a result, quantum computers can do 2 things at once, or 4 things at once, or 8 things at once, or 1,000,000 things at once, or 2 to the 300 things at once. And I picked 2 to the 300 because that's equal to the number of particles in the universe. So a quantum computer with 300 bits can do as many things as there are particles in the universe. So how predictable is it that it's going to do the same thing every time? Well, let me actually step back from that just a second, and because I want to make sure that people understand what's going on here. If I just have this state which is 0 and 1 at the same time, and I ask, say it's an electron here and there at the same time, and I make a measurement of where the electron is. I ask the electron, are you here or are you there? Then half the time the electron will show up here, half the time it will show up there, and it's purely chance when it shows up. So there's this intrinsic chanciness in quantum mechanics. God plays dice, or this is how God plays dice. I mean, all this talk about God, I think is a little unfair to God, whether she exists or not. Okay, so God plays dice. Chanciness gets introduced at the quantum mechanical level. However, that kind of chanciness is different from the kind of chanciness, any errors that are induced here. So here are if we want to say, if this bit is 0, add 2 plus 2, that depends on our ability to manipulate and talk with these individual atoms. And that can be done to very high degrees of precision. Each operation can take place to an accuracy of 99.8% accuracy. So we can actually add 2 plus 2 in a pretty much bug-free fashion. And similarly, we can add 3 plus 1 in a bug-free fashion, and that, as a result, we can make a quantum computer that does this and that at the same time in a pretty much bug-free fashion. That's not to say it's all fun and games down at that level, because in fact, remember that the thing that makes it choose to be either 0 or 1 is something coming in and getting information about it, something measuring it. That doesn't have to be a human being going and measuring if the electron is here or there. If another electron comes along and interacts with this electron and figures out, oh, is it here or is it there, which is pretty easy, which can be pretty easy, then it will be the bit will be either 0 or 1, and you're no longer doing adding 2 plus 2 and adding 3 plus 1 at the same time. You're doing either one or the other, and a classical computer can do that. So you have to be very careful when you build a quantum computer to insulate your quantum bits from the surrounding, to make sure that there's nothing out there that's peeking in. This is why it's considered to be very rude to look at somebody else's quantum computer when they're performing a computation. It's a modesty and privacy issue. There's actually, in fact, there's a whole continuum of states, because you could have it be either there, or you could have it be, less here and more there. So it can vary continuously. So I told you that there's this discrete, chunky quality to quantum mechanics, that things that are continuous appear to be discrete, but there's also this continuous aspect to quantum mechanics. It becomes from this wave-like nature. And it's that continuous aspect that we're playing with when we play these games with atoms and make them compute. So in the end, you're only going to get one answer. And the whole trick of quantum computation is at the end to combine these waves in the final analysis so you can get some interesting answer. In this case, the answer was 4 each time, okay? But in fact, there are problems like a famous problem that quantum computers can solve that classical computers can't is breaking codes, the codes that you use when you buy something over the internet. So, if I suppose I buy green coffee beans, let's say, over the internet, that's something I foolishly have been doing recently, the coffee corral sends me what's called a public key, and I can use that to encrypt my credit card information, send it off to Coffee Corral, and only they possess the private key. But if you had a quantum computer, you could break this code because you could deduce the private key from the public key. So if you had a quantum computer, you could do this. And the way that you do this is you essentially make these waves interfere with each other. So because these are waves, like for instance, imagine this is something that used to happen to me a lot when my kids were younger. Suppose my daughter Emma is in this side of the bathtub and makes a wave going this way, and Zoe, who's over in this side of the bathtub, makes a wave that's going that way. And I'm sitting here in the middle. I don't have that much hair, okay? I'm sitting here in the middle. When these two waves come together, they exhibit what's called positive interference and splash out all over me, right? So you have to be, the tricky part about quantum computation is getting this positive interference to happen. But if you can do that, then you can do things that, would strike fear in the hearts of, eBay, the CIA, the NSA, and other A's with so this would be a very disruptive technology, quantum computation. Luckily, in fact, it's handled in the United States partly by the Disruptive Technologies Office. And I definitely want a black jumpsuit that says Disruptive Technologies Office on it. I mean, come on, what could be better than that? But they refuse to make them for me. I can't, just a hat, please. Okay. All right. So, how do you build quantum computers? Well, there's lots of ways of doing it. For instance, you can take just a bunch of atoms in a molecule. This is my picture of a molecule. And basically, you zap them with microwaves. Each atom in this molecule listens to microwaves, responds to microwaves of a slightly different frequency. It's as if they listen to different radio stations. So for instance, this atom over here could listen to 89.7 WGBH in Boston. This one could listen to 102.5 WCRB. So if I put on light at 89.7, million times a 7, this atom will flip. So when I say flip, I mean these things are actually little magnets like we had before, north and south. So when I put on light, I flip these magnets because the nuclei of atoms have magnets on them. This is the 102.5, the WCRB one. When I put on light at 102.5, this atom will flip. And then the atoms are all interacting with each other already because they're down there, a billionth of a 10 angstrom apart, 1/10 billionth of a meter apart. And if you're sensitive to the way they interact with each other and are careful about how you flip them, you can make them compute. It's not so hard. And this is what I showed a little more than 10 years ago. the notion of doing quantum computation was proposed back in the early 80s by Richard Feynman, Paul Benioff, David Deutsch, and others. But nobody had a clue how you might build a quantum computer. And in 1992 and 1993, I showed that, oh, if you just take off-the-shelf stuff, atoms and molecules, zap them with lasers and microwaves, but are sensitive to the way that you zap them, then you can make them compute. And now there are many, many people around, thousands of groups around the world building quantum computers. It's hard, but it's not that hard, okay? And by the way, I should mention at the risk of, I don't want to go over time, I should finish up soon, but I've tried to be sensitive in my language about here, like you were sensitive to my feelings before. Even Americans can occasionally be sensitive, all right? So I was at a wedding a few years ago of my cousin, who's a social anthropologist. And I was seated at a table of all social anthropologists, and I was seated next to Barbara Ehrenreich, who is a very left-wing social critic in the United States. And she asked me what I did. I said, oh, well, I take the innate information processing ability of atoms, and I exploit that to make them compute. And they all went, oh, that sounds so horrible, so exploitative, that's awful. Can't someone stop this right now? But then they calmed down a bit. And Barbara Ehrenreich knows, actually, she has a degree in chemistry. She knows a lot about this stuff. So they got me to talk about it some more. And they said, oh, okay. And the person she was with, an older black, African-American activist from Greensboro, North Carolina, said to me, Seth, next time you describe what you do to people, I suggest you say that you empower atoms to compute. It was a great moment in my life because I went, suddenly for years I'd been an exploiter of atoms, and all of a sudden I went in 10 seconds to being an empowerer of atoms. It was wonderful. Just like the people at the PI, I should say, empowerers of atoms right and left. There are lots of other ways of doing it. You can set up a bunch of atoms, trap them in an optical cavity. This is my picture of an optical cavity. It's like a coffee can that holds photons, and zap them with lasers. Zap them with lasers. That's a good way to make things compute. You can make little superconducting circuits. This is extremely sketchy, as you can see. These are superconducting circuits where you can get 1 billion electrons going this way around the circuit and also going that way around the circuit at the same time. So going this way around the circuit is 0, going that way around the circuit is 1, and they can all be going this way and that way at the same time. And don't ask me how that is. I just know that you can do it, right? I don't know how it can be. What are other techniques? Well, you can build little quantum dots. This is a picture of a quantum dot. And you can have electrons that hop from one side to another. Remember, electrons are blue in my cosmos. Also, they didn't give me any yellow here, so I can't draw them as yellow. There are lots of ways of doing this. Oh, and you can hook them up. You can hook these up to quantum communication lines. And you can have photons coming from far away. And you can move quantum bits from here to places hundreds of kilometers distant. So this is something that not only can be done, but is being done, building quantum computers, making them and exploring their properties. So a question that some American audiences have asked me at this point is, so what? Right? Right? So what? So you build these quantum computers, big deal. Well, building quantum computers is, the reason we do it is, the reason all engineers do stuff is because it's fun, right? And we can, right? This is why engineers are dangerous, and when they start using terms like exploiting things to make stuff happen, you should really be careful about them, right? We're doing this because we can. We can build the quantum technologies to do this. And actually, I should say, in my personal case, even though, I do have money to do public research from places like the NSA and the Disruptive Technologies Office, all right, they want to build big quantum computers to factor numbers and break public key cryptosystems. I do this because this is a way to understand what's happening in the universe at its most microscopic and fundamental scales. These quantum computers we built, you couldn't make a smaller computer, you couldn't make one that stored information with less, because there isn't any less to go to. Once you're down at the level of 1 quantum, 1 bit, you have nothing below that. 0 quanta, 0 bits, right? So we're actually looking at the universe at its most microscopic scale, making things compute. And indeed, in doing that, again, we're simply hacking into the underlying computational ability of the universe. The universe was computing already and has been for 13.8 billion years, computing lots and lots and lots of stuff, most of it just little random motions of molecules, but some of it, the composition of my DNA, all right? And some of it, what's going on inside my head and what's going on inside your head. So there's all sorts of interesting, well, maybe interesting is subjective, all sorts of interesting things going on out there because of this computational nature of the universe. And I think this is important for understanding what the universe is and what it has done in the past and what it will do in the future. In particular, I claim that this computational ability of the universe allows us to understand something which the ordinary laws of physics don't. Why is the universe complex? Where did all this information come to? I mean, things are out of control, right? It's incredibly complex. It's amazing. It's remarkable. It's wonderful. It's horrible. It's all those things, but huge amounts of stuff is going on. It's not simple. Where did all these bits come from? Well, now you actually know where bits come from in the universe. Because remember these quantum bits where electrons are here and there at the same time? If they interact with other electrons, then suddenly they're here or there at the same time. A bit is essentially produced. You go from having no bits to having a bit. For example, here is a typical kind of bit in the early universe. Here is a quantum bit where there's a little tiny overdensity of energy here and a little tiny overdensity of energy there. Let's say here is here, and there is 100 million light years off in that direction. Now, why is our universe here rather than over there? Well, because in this component of the wave, as time goes on, time always goes up in general relativity. I like this, because for engineers, time goes from left to right. For physicists, for some reason, it goes from right to left. But for people studying the universe as a whole, it always goes from bottom to top, which I think is really lovely, because it means the universe is growing, right, and who knows what might happen. So as time goes on, stuff clumps around here. Okay? The universe is clumpy. As they used to say in my high school, gravity sucks, excuse me. Over here in this component starts clumping, and then after a while it clumps more and more, and after a while you get galaxies and stars, planets, etc. But the information that caused the universe, our galaxy, to be here rather than 100 million light years off in that direction came from some little tiny quantum fluctuation, some little tiny quantum bit back at the very beginning of the universe. So what's happening is the universe is computing, and random bits are being injected into it constantly from these little tiny quantum fluctuations. This information is coming from quantum mechanics. It's coming from God playing dice. Now, you may say, but hold it. These bits are just showing up random, here or there at random. How is that an explanation for what we see? Well, that on its own is not. In fact, the notion that maybe the universe just arose completely at random was thought about quite a lot at the end of the 19th century, and people rejected it. But now let's look at another picture. And I don't know the origins of this picture. It's been around for, since the 80s. Monkeys typing into a computer. So take these random strings of bits that the monkeys generate and use them as instructions for a computer. Right? Because remember, that's how computers interpret bits. They take bit, 0 means do this, 1 means do that. So instead of just taking random gobbledygook, take that random gobbledygook and interpret it. Have the computer assign it meaning, all right? What happens then? Well, there's a rather elegant and lovely mathematical theory called the theory of algorithmic information, which is essentially the theory of monkeys typing into computers. If you have monkeys that type into computers, what's the probability of interesting things happen? And it's a beautiful theory, and you can prove mathematically that these monkeys have a very good chance of producing all sorts of complex things. Why is that? Well, remember, the initial state of the universe had almost no information in it, and the laws of physics are very concise. They could have only a few bits. The monkeys could hit on that, right? They could easily hit on the laws of physics. Another thing that they might start doing is instruct this computer to produce all mathematical theorems, prove them all provable mathematical theorems. Quite a big order, but that would happen. In fact, there are very short programs that allow that to happen. Or create all possible mathematical structures, all possible describable mathematical structures. Or create the laws of chemistry, okay? The monkeys will have a good chance of doing this. Monkeys typing into computers as opposed to monkeys typing into typewriters. So you see, for this to explain where all this complexity comes from, we need two things. We need a computer, and we need monkeys, okay? So, by the way, this was actually an experiment that was done at the University of Nottingham. They took monkeys at the Nottingham Zoo, crested macaques, I think, and then they gave them a computer covered with plastic and taught them to type on it. Actually, first, the monkeys, it's a lucky thing they covered with plastic, because the first thing they did was defecate and urinate on the computer. And then they pounded on it. Finally, they figured out how to type. And at that point, they exhibited a fondness for the letter S, is what I understand. But we have a computer. It's the universe itself. It's been known for 150 years the universe is computing, it's processing information. And we have monkeys. We have these little quantum fluctuations that program the universe. Because if you trace, for instance, why is my DNA different from my brother's? You know, okay, well, my parents had sex, their genes got scrambled up together, and I got dealt one hand of DNA, and my brother got dealt another hand of DNA, right? One combination versus another. Where did those little differences come from? Those are little tiny quantum accidents, if you trace them back to their origin, AKA monkeys, right? These little quantum accidents monkeyed with my DNA. I got what I got, he got what he got. And believe me, my brother and I argue a lot over this issue. Okay, in other words, what does this theory of the computing universe give us that we don't have already? It gives us an explanation for why we are here and everything else, with all of its wonder and horror and majesty and little humble things going on. All this complexity comes because the universe is computing. If you have something that's computing and it's being programmed by little random fluctuations, then you shouldn't be surprised that things like stars and galaxies form, that things like life forms, that things like human beings arise and start speaking and start making computers themselves. That is not a surprise. In other words, not only, if you have monkeys typing into a computer, not only do they not generate nothing, like monkeys typing into a typewriter, in fact, they could generate everything. And that's all I have to say.
Support Ontario's public television. Donate at tvo.org.